Welcome to The Explainer. Today, we are diving into the fascinating math and engineering behind modern AI chatbots. If you've ever wondered what is actually happening under the hood when a model generates text, well, we're going to look at the raw mechanics together right now. Let's jump in. So I want to hook you immediately with a pretty good question. Is your AI actually thinking? When you type a prompt and watch this beautifully structured, highly logical essay stream across your screen, it feels incredibly human, right? It feels like real comprehension. But as we're going to see today, what you are witnessing isn't cognitive reasoning in the human sense at all. It is something entirely different. It's deeply mathematical, and honestly, it's just as fascinating. Section 1. The core illusion. Pattern compression versus comprehension. Take a look at the stark contrast here between human cognition and machine training. As humans, we learn through real-time understanding. We have goals, we interact continuously with our environment, and we have a persistent memory of individual events. Large language models, or LLMs, do not. The bedrock of an LLM is literally just statistical pattern compression. They learn almost entirely offline by adjusting billions and sometimes trillions of numerical weights using gradient descent. Their absolute sole objective during this massive training phase over vast amounts of text is just to minimize their prediction error for the very next word. Imagine your entire life goal being to just never, ever mess up the next word in a sentence. It's not fact storage, it's not real-time comprehension, it's purely statistical likelihood. Section 2. Tokens, the language of math. Okay, let's dive into this. If these models only understand math, how do they process our messy, unstructured human language? Well, let's sketch out the exact engineering pipeline. Models don't process raw text strings directly. First, we take the raw text and run it through a process called byte pair encoding, or BPE. BPE basically scans the text and merges the most frequent adjacent characters into subwords. So common words might become a single subword, while rare words get chopped up into fragments. Next, these subwords are mapped into a vocabulary of discrete integer tokens. Think of it like a giant lookup table that can have anywhere from 32,000 to over 200,000 unique entries. Finally, those integers are translated into continuous vector embeddings, which places every single token into a high-dimensional mathematical space where the model can actually do math on it. And here's a fun little fact. Because words are chopped into these integer chunks, this is exactly why AI models notoriously struggle with simple tasks like spelling words backwards or counting the characters in a word. They don't actually see the letters, they just see the token. Section 3. The next token engine, the ultimate guessing game. So once our text is mathematically translated, we feed it into what is essentially the ultimate guessing game. Modern generative models are what we call autoregressive. You can think of this as a seamless feedback loop. The model looks at a sequence of tokens, like the capital of France is, and predicts a probability distribution for the next token. If it guesses Paris, that output is then immediately fed right back into the context as a brand new input. It generates an output sequence, just one single step, one single token at a time. The output of step 1 perfectly seamlessly becomes the input of step 2, over and over again. Let's draw out the mathematical flow of that exact prediction. During training, the tokens go through a forward pass through the network's layers. The model then outputs a logits vector, which is basically one raw score for every single token in its entire vocabulary. That's its guess for the next word. We then apply a math function called softmax to convert those raw scores into a clean probability distribution that adds up to 100%. Finally, we calculate the cross-entropy loss. Now, this is a totally crucial metric. It measures exactly how surprised the model is by the actual correct token that appeared in the training data. The model then uses backpropagation and an optimizer to slightly tweak its billions of weights so it'll be just a little less surprised the next time around. Section 4. Attention. Connecting the dots. So, the crucial point is, how does the model actually make good guesses? Because a raw guessing mechanism is completely useless without context. And this brilliantly illustrates the breakthrough that made all of this possible, the 2017 transformer architecture. Unlike older sequential models that processed words one by one and basically forgot earlier context, the transformer stack processes entire sequences simultaneously. It's highly parallelizable, and it captures long-range dependencies across the text using something called global attention. The real secret sauce inside that transformer is the self-attention mechanism. It acts like a highly dynamic information retrieval system. Every single token in a sequence generates 3 vectors, a query, a key, and a value.
Think of the query as a token basically asking, hey, what information do I need right now from the rest of the sentence to understand my role? The key is every other token broadcasting, here is the information I have to offer. The model then calculates attention scores based on how well the queries and keys match up, and then pulls in the value, which is the actual retrieved information. This is exactly how a word like mole can completely disambiguate itself. By paying attention to the surrounding words, its mathematical embedding is dynamically refined to mean either a burrowing animal in the dirt, a chemistry measurement, or a mark on your skin. It's like a giant puzzle constantly solving itself.
Section 5. From predictor to assistant, the final alignment. Let's move to and see how this builds. Let's see how this actually builds into the products we use every day. Because honestly, simply predicting the next word of internet text doesn't magically make a helpful chatbot. If you prompt a raw-based model with a question, it might just predict another question to follow it, instead of actually answering you. Transforming a raw text completion engine into a reliable assistant is a massive multi-stage pipeline. Phase 1 is pre-training. This is the computationally massive part where the model ingests trillions of tokens just to learn the statistical structure of language, grammar, and facts. This creates the base model. Phase 2 is supervised fine-tuning, or SFT. Here, we train the model on tens of thousands of curated instruction and response pairs. This teaches the model the actual format of being a helpful assistant. And finally, Phase 3 is alignment. Using techniques like reinforcement learning from human feedback or direct preference optimization, we shape the model's stylistic boundaries. But here is the single most important conceptual reality check for absolutely anyone using these systems today. Weights are frozen at inference. When you are chatting with a deployed model, it is not permanently learning from your conversation. There is no persistent memory being formed. Your prompt is just passing through the network in a transient, forward pass-only adaptation called in-context learning. The second you clear that chat window, that adaptation vanishes entirely. It cannot remember you because its underlying mathematical parameters are completely locked. Which leaves us with this final, truly profound thought to sketch out. We've established that these models are, at their core, just optimizing loss functions, computing attention scores across vectors, and statistically predicting the next token. They do not possess human understanding. But as these models scale up to trillions of parameters, they actually begin to exhibit emergent capabilities, things like reasoning, arithmetic, complex coding, and it's all born from the incredibly simple objective of just predicting the next word. It really begs the question. If a machine can perfectly simulate understanding just by predicting the next word perfectly, from our perspective on the outside, what's the difference? Thank you for exploring the mechanics of language models with me today on The Explainer. Keep questioning the world around you, and I will see you next time.